Hello and welcome to our 6.3 to 6.4 video. Today we are talking about binomial random variables. So this is another type of random variable now. It counts as a discrete random variable. However, with these special ones, it's actually easier to calculate probabilities with them. So that's why we have this special binomial type. So when is a random variable binomial? Here are the rules. I made it stand for BINS so that it's easy to remember for the 4 rules. Okay, the first rule is that for the B, it stands for binary. So binary meaning like there's only 2 options. Outcomes can be either considered a success or a failure. So you either did it or you didn't. There's no like in between like a maybe option or anything like that. So you only have 2 options, success or failure. The second rule is that each trial needs to be independent. So meaning, remember, independence means that when you do something the first time, it shouldn't affect the probability of you doing it again the second time. So each time we repeat something, each trial that we do should be independent of the next. The third rule is that N is going to stand for the total number of trials, which means you're not repeating something a bajillion times. Like it has to have a set number. There's a stopping point. So the problem should say you're doing this 10 times, or there's like 6 people that you're picking from, or something like that. So there's like a set number. It's not like you can go on forever. And finally, the S stands for the same probability of success. So that means kind of like it has to do with the whole independent thing. Because each trial is independent, then the probability of success shouldn't be changing from trial to trial. So each repetition that you do should not be changing. So let's take a look at a couple scenarios to see whether they are binomial or not, and then that gives you a little bit of a better example as to like what binomial actually means. So this first example, genetics says that the genes children receive from their parents are independent from one child to another. So automatically they told us independent from one child to another. Each child of a particular set of parents has probability 0.25 of having type O blood. Suppose these parents have 5 children, count the number of children with type O blood. Okay, so based on this problem, we know that there's a probability of success. Our success is having type O blood, because that's what we want. And then the parents have 5 children, so that tells us we have a total number of trials. We're only going to repeat like having a kid 5 times. And then because that probability of success is the same, it's 0.25 every time, it's independent from each other, then this makes it binomial. Okay, the second example, we have a standard deck of 52 playing cards. Turn over the first 10 cards one at a time, record the number of aces you observe. Okay, so we know we have N, because we're only going to turn over 10 cards. So it's not like they're telling us to go on forever and do the whole deck or anything like that. So N equals 10 here. We're looking for the number of aces. So getting an ace would be a success for us. Not getting an ace would be a failure. But the only thing here is we don't have independent trials, and neither do we have the same probability of success. Because as we turn over cards, if there's 52 playing cards total, as we turn over a card, it's not like we cover it back up or stick it back in the pile or anything like that. So then the next time we turn over a card, the probability of getting an ace is different now because you have less cards in your sample space. So for this one is not binomial because we don't have independent trials. Alright, so let's get into the good stuff. Now that we know when something is binomial and when it's not, now we can actually talk about the probabilities for them. So whenever we're dealing with binomial random variables, there is a formula to calculate probabilities. It looks like this. Here's our formula. So we have probability of X. So X stands for how many successes you want, and that'll be given to you in the question. To find it, we're going to find NCX. So remember, this was the combinations that we had last chapter. So N is the total number of times we're doing something. We talked about that earlier, is like how many trials that you're going to have total. C, and then for the combinations, X is whatever number that they're asking about. Times. P stands for the probability of success. So like in the earlier example about having type O blood, the probability of success would have been 0.25. Raised to the X power, again, X stands for how many successes you want, times 1 minus P. So you can think about this as like how many failures do you want really? Because if P is the probability of success, 1 minus P would have been the opposite of a success, so a failure. So this is how many failures you want, N minus X. So this would be how you do it by hand. Obviously we have a calculator way because we are statisticians, we love our calculator. In the calculator, we can have our calculator calculate this whole formula for us by going to second vars. So second, and then the vars button is right next to the clear button. It takes you to something like this at the top. It says distribution. You're going to scroll all the way down until you see something called Binomial PDF. Right here. For me, it's letter A. For your calculator, it might be slightly different. But you're looking for one that says Binomial PDF. Hit enter. And so, again, depending on your calculator, it may or may not ask you for these things. If it doesn't, you're just typing these things in this order. N, comma, P, comma, X. So N is how many trials we have. P is your probability of success. X value is the number that they're asking you for. And then hit paste, enter, and then it'll give you the probability. So if your calculator doesn't give you these options, you're typing each of these letters with commas in between. So remember, the comma button is right above the 7, and then you would hit enter, same way as before. So let's do some examples so we can see how to use this. So we're back at the type O blood example. We've got a probability of success of 0.25. These parents have 5 children, so we know N is going to be 5. Let X be the number of children with type O blood. Find the probability that X equals 3. So here in the problem, we're saying we're going to use 3 as our X variable. All right, so for this problem, we know N equals 5 because we're having 5 children total, so that's the first number that we type in. And then our P, our probability of success, was the 0.25. Type that in. And then we're being asked about X equals 3, so the X value for us is going to be 3. Hit enter, enter. So there's our probability. So all your calculator did was use that formula to calculate this. And again, if you have like the older calculator where it doesn't list all the things that you need to type out, then what you're typing out should look like this. Binomial PDF of 5, 0.25, 3. Hit enter, you should get the same thing. And just as with any of our other probabilities that we've been doing, we're just going to stick to the 4 decimal places. Okay, let's try another problem. So the next one, same situation, but here we are looking to see the probability that none of the children have type O blood. None of the children means that we're asking about the number 0 then. So in this problem, X is going to be 0, but N is still 5, P is still 0.25. So we can find the probability in our calculator, second vars again, scroll down until we see Binomial PDF. So sometimes your calculator saves your numbers, it's kind of nice. We have 5 as our trials, 0.25 as your probability of success, but this time our X value is 0. Paste, enter. So now the probability of having none of the children have type O blood is like 23.73%. So on a quiz or a test, this is exactly the amount of work I want you to show. We're using Binomial PDF, so tell me that, and then tell me what numbers you're using for N, P, and X, and then give me the probability. That's pretty much it. So the next one, this time we're looking for less than 3 children have type O blood. So this one's going to be a little different because they're not just asking us about just one number now. They're not saying like X equals 3 or X equals 0 like we had before. This time it's less than 3. So numbers that are less than 3 would be like 2, 1, 0. When we deal with binomial problems, the smallest number you can have as the number of successes is 0. Because it doesn't make sense to have like a negative number of successes. So 0 successes is the smallest you can have, and then it goes all the way up to whatever N is, because that's like the max amount of successes you can have. So here we're looking for less than 3, so we're always going to start at 0, and then we want 1 and 2. We're not including 3 because when we say less than 3, it doesn't include the 3. So we can find the probability of 0, find the probability when X equals 1 using Binomial PDF again, and then find the probability of X equals 2 using Binomial PDF again, and then add all 3 of those numbers together. So that's one way to do it. Your calculator, of course, has an easier way to do things. So if you go to second vars, and scroll all the way down to see Binomial PDF again. If you go one more down, there's a Binomial CDF. So the C stands for cumulative, meaning it'll add things for you. So this is kind of nice. For this problem, we're going to use Binomial CDF. When you hit enter, it actually asks you for the same things that it asked you for before. The only thing is when you type in your X value, so let me type in my trials is 5.25 for my P. This time if I type in 2 as my X value, the calculator will automatically add up the probabilities for X equals 0, X equals 1, and X equals 2 together. And that's how you tell it when to stop. So we're telling our calculator, I only want numbers up until 2, and then add them up for me. So when I hit enter, it's done that. Just notice how it's a much bigger probability because it added up a bunch of probabilities for you. So this is the shortcut for when you have to add things together. Okay, so I tried to write out a little explanation here. So just to recap, we are trying to find the probability that X is less than 3, which really means we want numbers 0, 1, and 2, because those are the numbers that are less than 3. So we could do Binomial PDF like the way we did before. We just do this 3 separate times, so you'd have to type in Binomial PDF, type this in, find it for 0, then do it again where X equals 1, and do it again where X equals 2. Take all those 3 probabilities and add them together. It'll get you the same answer. Or use our shortcut, Binomial CDF, where N equals 5, P equals 0.25, X equals 2, because that's the highest number of what we're adding together. And then it just adds it for us to get that 0.8965 when we round to 4 decimal places. Okay, sounds kind of nice. Next, this time we are looking for the probability that at most 4 children have type O blood. So now we need to understand what at most means. At most means 4 is the biggest number. So we want numbers that are less than 4, but 4 is the max, nothing above 4, which means we want 0, 1, 2, 3, and 4. So those numbers, we can add them all together, or again, since we're adding stuff together, we can have our calculator add it using the Binomial CDF. So this time the biggest number we want is 4, so our X value here is going to be 4. So I'm going to go find Binomial CDF again. I'm actually going to just scroll up. That's less things to scroll through. So Binomial CDF. So again, pay attention to whether you're using PDF or CDF and which one you've chosen. It's a common mistake. So N is 5, P is 0.25, X value this time is going to be 4. Enter. And we get 0.9990. So much bigger probability this time. But there we go. All right, this next one is going to be a little different because this time I want to find the probability that more than one child has type O blood. Okay, so this time we're not talking about numbers that are smaller than whatever number they're asking about. We're talking about like greater than, right? So greater than 1 means we want 2 and above. But the max amount that we can go to is 5 because our N equals 5 here, so the max amount of successes you can have is 5. So really we want 2, 3, 4, and 5. As the number of successes that we want. So we can do that using our Binomial PDF. If we find the Binomial PDF of X equals 2, find the Binomial PDF of X equals 3, do the same thing for 4 and for 5, add up all those probabilities together. We can do that. CDF, though, doesn't quite work the same here because when we do Binomial CDF, because even though that's the shortcut, your calculator only adds up probabilities starting at 0. We didn't even want 0. We only want 2 through 5 for this problem. So if we don't want 0, we also don't want 1 in this case because we're starting at 2. So we didn't want 0, we didn't want 1. So if we don't want 0 and 1, we could figure out what those probabilities are, but then subtract it from 1. Because remember, in a probability distribution, all the probabilities, all your different outcomes should add up to 1. So if you found the probabilities for 0, for 1, for 2, for 3, all the way through 5, all those probabilities together should add up to 1. So if you can figure out what numbers you don't want, then you can subtract it out, and that would give you the probabilities for what you do want. So we're basically saying, if I want the probability that X is greater than 1, then I don't want 0 and 1 because I want 2 through 5. 0 and 1, though, is something that your calculator can find, because remember, binomial CDF starts counting at 0, goes up to whatever number you tell it to. So if we tell our calculator 1 for when we do binomial CDF, it'll add up 0 and 1 together and find us that probability. So if we do 1 minus binomial CDF of our n equals 5, and then p is 0.25, and x is 1, then this should leave us with the probabilities for 2 through 5 that we wanted. So, calculator time. Let's first find binomial CDF of 0 through and 1. Okay, so for 0 and 1 added together, it's 0.6328. We're going to do 1 minus that, and that'll give us the probabilities for everything else that we want, 2 through 5. So this is going to be our final answer, 0.3672, if we round correctly. And that's how we find probabilities that are more than or anything greater than. Okay, one more of these types of examples. This time I want the probability that at least 2 children have type O blood. So let's think about the words at least 2. So again, this is 2 or more is what we mean when we say at least 2. So 2 or more means I want 2, 3, 4, 5 again. Should give us the same answer here. So pay attention. More than 1 and at least 2 mean the exact same thing. Just a nice little trick, but it does make you pay attention to things. So the process for finding our probability is going to be exactly the same. Since we want 2 through 5, we don't want 0 and 1. And so you would do 1 minus binomial CDF of 1, and then that'll get you that answer. Let's change it up a little bit just so we have a different example here. Let's change this to at least 4 children have type O blood. Okay, so pretend you can read that. It's really hard to draw on a computer. Pretend this is the word number 4. At least 4 children have type O blood. So at least 4 means we want 4 or more. 4 or more, we only go up to 5 in this case, because remember, n equals 5 in this problem. So really, we just want 4 or 5. So again, if you want, you can take binomial PDF of 4, binomial PDF of 5, and then just add them together. Or, if we want at least 4, that means we don't want the numbers below 4. So from 0, 1, 2, and 3, those are the numbers we don't want. So we can subtract that from 1 and get us our final answer by using the binomial CDF in our calculator. So here I'm spelling out, we got x is greater than or equal to 4 is what we want. So that means we don't want 0 to 3. So 1 minus binomial CDF, where x equals 3. Doing that in our calculator. This is the answer I get when I find binomial CDF of 3, but then we want 1 minus that to get us the 4 and the 5 that we want. So I end up with 0.0156, and that'll be our probability. All right, the last thing I want to talk about then is for binomial and random variables, we can actually calculate a mean and standard deviation as well. It's even easier than the mean and standard deviation formulas that we had from before. Because before we had to do everything in the calculator with the lists and everything. With a binomial random variable, the formulas are much easier. The formula for the mean is just n times p. So easy. So whatever your n is, your total number of trials, multiplied by p, your probability of success, that would give you the mean. For the standard deviation, again, just a simple formula. It's the square root of n times p times 1 minus p. So everything gets multiplied together, and then you square root the whole thing. So, example. Same problem. We have n equals 5, p equals 0.25, so find and interpret the mean and standard deviation. For the mean, we're just doing 5 times 0.25 as our n and our p. We get 1.25 from that. So that means, on average, if parents have 5 children, then on average 1.25 of those kids would have type O blood, because that was our success. If we're calculating the standard deviation, then following our formula, we have the square root of 5 times 0.25 times 1 minus 0.25. When you do that in your calculator, you end up with 0.9682. What this means is that the number of kids with type O blood would typically differ from the mean by 0.9682 kids. So usually standard deviation, we talk about something typically differing from the mean, and so that's what this is as well. I'm so sorry for my lights that keep turning off. My motion detector in here is terrible. That's the end of 6.3. Thanks for watching. Bye.